Hi there, I hope you're well. Today we're going to be talking about a very important subject, that is finding a particular solution to a differential equation when the equation is defined implicitly. And if you're not sure what implicitly means, it's just a fancy way of saying that we have x's and y's mixed together in the equation. This skill is fundamentally the same as finding the general solution to a differential equation, only there's one more step that we're going to have to consider. So if you're not sure how to find the general solution to a differential equation, why don't you go ahead and treat yourself and watch the Auducation video on how to find the general solution to a differential equation using the strategy of separation of variables. The big difference in finding a particular solution over a general solution is that not only does a particular solution's derivative have to be the differential equation, but it also needs to satisfy an initial condition on x and y. The steps for finding a particular solution are almost exactly the same as those for finding a general solution, with the exception of the last step. First, we have to isolate all the y terms, including dy, on one side of the equals. Then, we need to integrate both sides of the equation. And instead of solving for y in our last step, what we're going to do is we're going to plug in the values from the initial condition into our general solution, and then solve for c. From there, it may be possible to solve for y, but depending on what we need, we may just leave it as it is. So without further ado, let's go ahead and take a look at some examples. Our first example asks us to find the particular solution to the differential equation dy over dx equals cosine squared of y times secant of x times tangent of x that satisfies the initial condition pi over 3, pi over 4. If you're curious, our particular solution is the equation whose graph will pass through the point pi over 3, pi over 4, and whose derivative is going to equal dy over dx. And now why don't we just go ahead and follow the steps and get ourselves a particular solution. Our first order of business will be to isolate the y's. We'll do this by multiplying both sides by dx to move the dx over, and then dividing both sides by cosine squared of y to get rid of that cosine term. I almost feel like we need elevator music here. Not that this isn't soothing enough as it is. In any case, the dx's will cross off and so will our cosines, and our next step will look like 1 over cosine squared of y times dy equals secant of x times tangent of x times dx. There we go. I don't think I need to convince you that 1 over cosine squared is not a good thing to have, so we'll use the reciprocal property to change it into secant squared of y dy, and we haven't changed our right-hand side. We'll keep that the same as secant of x times tan of x times dx. Now that we've isolated our y terms, we can move on to the second step, which is to take the integral of both sides. How you liking that elevator music? Pretty soothing, right? It certainly makes sitting through this calculus just a little easier. Okay, now that that's all said and done, we can go ahead and take the actual antiderivatives here. The antiderivative of secant squared will be tangent of y, and the antiderivative of secant tan is going to be secant of x, and then of course we need our pal plus c. And this is where we part from our general solution procedure. Here we want to incorporate our initial condition back into our equation, rather than solving for y right away. So what does that mean? It means plug in pi over 4 for y and pi over 3 for x. We have tan of pi over 4 equals secant of pi over 3 plus c. And evaluate. Tan of pi over 4 is equal to 1, secant of pi over 3 is 2, plus c. Now we minus our 2 from both sides. That'll cancel out the 2's over here, and we get negative 1 equals c. Incorporating this back into our general solution, what we're going to get is tangent of y equals secant of x, and then c was negative 1. There it is. That's a solution. Or, if you wanted an explicit rule solved for y, just take the inverse tangent of both sides. So y is equal to arctan of the quantity secant of x minus 1. Whichever one you use really depends on the context, but just be satisfied that we could find a solution for now. Let's take a look at another example. Okay, moving on, we're trying to find the particular solution to dy over dx equals negative xy that satisfies the initial condition 6, 2. We start the same by isolating our y's. Multiply both sides by dx again, and then we'll divide everything by y. Ooh, a little funky this time. And of course our terms will cross off again on both sides, and our next step is going to give us 1 over y dy equals negative x dx. And now that our y's are isolated, we can go ahead and jump into our integration step. And you know what that means. More elevator music. Not so nice weather we've been having lately, is it? Okay, that's enough of that for now. Anyway, the antiderivative of 1 over y is the natural log of the absolute value of y, and then the antiderivative of negative x is negative 1/2 x squared, and of course plus c. Having y inside of a natural log is algebraically going to be kind of challenging for us, so it's actually going to be in our favor to solve for y this time. Fortunately, all we have to do is translate to the exponential statement e to the negative 1/2 x squared plus c. And now we'll use some of the properties of exponents to take that c out of the exponent position. A sum in the exponent results from the product of like bases, so we'll have e to the negative 1/2 x squared times e to the c. We're going to change the order of this now. The reason for that is because e to the c is e to a constant, which is itself a constant. And we can replace that with something else a little bit more general, like, I don't know, y equals big C e to the negative 1/2 x squared. This general solution is going to be much easier to incorporate our initial condition into to find our particular solution. So we plug in 2 for y and 6 for x, and that will give us 2 equals c times e to the negative 1/2 times 6 squared. 2 stays the same. C equals negative 1/2 times 36. And we get 2 equals c times e to the negative 18. We will then divide both sides by e to the negative 18, like this, and this. And so we get a solution for c. 2 over e to the negative 18 equals c, but we can change that negative exponent by switching its position. In other words, 2 times e to the 18th is c. We'll incorporate this back into the general solution by substituting it for c, so we get y equals 2e to the 18th times e to the negative 1/2 x squared, and we can use those same exponent rules from before to make one single exponent term, e to the negative 1/2 x squared plus 18. And this is our particular solution in this problem. I know it's been a little bit of a long haul, but let's take a look at one last example. Our final example problem asks us to find the particular solution to dy over dx equals e to the x plus y that satisfies the initial condition 1, 0. Now we may look at this and initially be concerned about the fact that both x and y are in the exponent position, but we can use the same rules of exponents that we used in the last example to break this off into 2 separate exponential statements that we can then use to isolate our y's. Remember, a sum in the exponent is the same as the product of like bases, so we're going to go ahead and rewrite the right-hand side of our equation as e to the x times e to the y. And then, just like before, we'll multiply both sides by dx and divide both sides by e to the y, isolating our y terms. And then, of course, our dx's cancel out, and so do our e to the y's. And that brings us to our next step here. We have 1 over e to the y dy equals e to the x dx. 1 over e to the y isn't ideal, so we can rewrite this as e to the negative y dy, and that'll make our integration just a little bit more straightforward for us. And of course, the right-hand side remains as e to the x. Our y's are isolated, and so we move on to our integration step, so we take the integral of both sides like so. And there we are. Now we'll go ahead and take the antiderivative of both sides. Now you may have had to use integration by substitution to get this, but the antiderivative of e to the negative y is negative e to the negative y, and the antiderivative of e to the x is e to the x plus c. Now we incorporate our initial condition here by plugging in 0 for y and 1 for x, and solving for c. And we get negative e to the negative 0 equals e to the 1 plus c. Now anything to the 0 power, whether it's positive or negative 0, is going to equal 1, and e to the 1 is just e. We will subtract our e from both sides because we want to get c by itself, and we are left with negative 1 minus e is equal to c. This gives us a particular solution of negative e to the negative y equals e to the x minus 1 minus e. And that's a perfectly good solution. But some people may want to have a particular solution that is explicitly solved for y. So here we go. Multiplying everything by negative 1 and changing up the order on the right-hand side gives us e to the negative y equals 1 plus e minus e to the x. Now we're going to take the natural log of both sides so that we can get that negative y out of the exponent position. So negative y is equal to the natural log of the right-hand side. Next, we multiply everything by negative 1 again, and that will give us a final explicit particular solution of negative natural log of 1 plus e minus e to the x. Now again, either one of these solutions is perfectly viable, and which one you need to use is going to depend on the context of the situation or your preference. And that's it, ladies and gentlemen. If you're trying to find the particular solution by using separation of variables, you start by isolating your y's, then you integrate, and then you plug in the values from your initial condition, solve for c, and reincorporate it back into the equation. Maybe sometimes you'll be asked to find an explicitly defined particular solution, and in those cases you would just use algebra to solve for y again. Most of the time, though, it's going to be up to your discretion. I hope you found this helpful, so thanks for joining, and we'll see you next time.